So, have you ever actually stopped to wonder how you build a skyscraper on a blockchain? Not physically, obviously, but digitally. I mean, how do you take a $50 million apartment complex or a multi-million-dollar private credit portfolio and safely encode it into a digital ledger without the whole thing completely falling apart? Well, welcome to this explainer. Today, we're going to expose the invisible underlying digital architecture that's powering the tokenization of real-world assets. It is complex, it's incredibly high stakes, and it's absolutely fascinating. Let's get into it.
Okay, let's dive into this. Here's our architect's blueprint for today. First, we're connecting the blockchain islands. Then, we'll solve the Oracle problem. Third, we'll look at the true costs of tokenization. And finally, securing the digital vault.
First up, connecting the blockchain islands and solving liquidity fragmentation. Let's look at this massive, kind of hidden hurdle in digital liquidity.
To really grasp the scale of this problem, think back to the early days of the internet. Way before we had a universal standard, you had these completely separate networks: ARPANET, CompuServe, AOL. A user on one couldn't easily talk to a user on another. And honestly, that's exactly the state of modern blockchains today. Think about it. If you tokenize a building on Ethereum, a portfolio of bonds on Solana, and a private equity fund on some private enterprise chain, they can't easily interact. They are completely trapped in isolated liquidity silos, which severely limits their potential.
Now, what's really interesting is how we actually solve that exact problem. Enter the Polygon AG layer. You can think of this as a sort of universal translator. It's a shared settlement layer that uses incredibly advanced cryptography, specifically zero-knowledge or ZK proofs, to bundle transactions from dozens of different blockchains and then settle them all on Ethereum in one single atomic transaction.
Let's break that down with an analogy, because it's a bit dense. Imagine a massive global corporation. All of its branches operate totally independently throughout the day, logging their own data. Then the global headquarters, which is the AG layer in this scenario, collects all those branch ledgers at the end of the day. It uses ZK proofs to instantly verify that everything is balanced and finalizes the whole shebang on one master public ledger. Because of this, thousands of distinct chains suddenly feel like one single unified network to the end user. It's brilliant. And for institutions that need maximum performance, well, they don't just use public chains. They build their own using the Enterprise CDK Aragon stack. This tech supports an absolutely incredible 5,500 transactions per second, which is right up there rivaling Visa. Plus, it lets companies create custom gas tokens. Seriously, a logistics company could literally launch a chain where transaction fees are paid in shipping credits. They basically build their own private hub for maximum control, and then connect it via the AG layer to the public spokes for deep liquidity. It's the ultimate strategic blueprint.
Moving on to part 2, solving the Oracle problem and establishing trust at the border. It's time to talk about the highly exploitable intersection where on-chain logic meets off-chain reality.
So here's a serious question for you. How does a blockchain actually know anything about the real world? By design, blockchains are these strict, deterministic, isolated environments. Every single node has to execute the exact same code and reach the exact same result. A smart contract cannot simply, Google the current price of a house or check an API for weather data. Why? Because different nodes might get slightly different answers, and that would break the entire consensus. To fix this, it requires an oracle.
The Oracle landscape has basically evolved into 3 distinct architectures. First, you have Chainlink's CCIP, which is the institutional standard. It uses a decentralized network of nodes that stake tokens to guarantee they're telling the truth. Then, the Python network takes a totally different route, pulling sub-second first-party data directly from over 90 major financial institutions. That's perfect for highly liquid assets. And finally, Redstone offers a pull-based model. This means smart contracts only request data when they actually need it, which drastically cuts costs for assets that don't need second-by-second updates.
But what about unique, illiquid assets? Things like commercial real estate. You can't exactly pull that from an exchange order book, right? So the crucial point here is this incredible innovation, the attestation oracle. This basically maps regulated professional human judgment directly onto the blockchain. A state-licensed appraiser physically inspects a property, signs their appraisal with a cryptographic private key, and submits it directly to the smart contract. That signature is unforgeable, meaning the entire chain of custody becomes perfectly transparent.
Which brings us to Section 3, the true costs of tokenization and Layer 2 economics. Because as beautiful as the theoretical magic of tokenization is, it absolutely has to survive contact with actual transaction fees.
Look, Ethereum mainnet is incredibly secure. That makes it the ultimate trust anchor for giants like BlackRock. But it is not a high-throughput transaction processor.
Minting a single token there can cost anywhere from $15 to $80. But doing that exact same operation on Polygon, Arbitrum, or Solana, that drops the cost down to fractions of a cent. Choosing the right chain literally dictates whether your asset is even viable to tokenize in the first place.
Let's make those economics a bit more visceral. $180,000. That is the crippling potential annual gas cost just to distribute monthly dividends to 10,000 token holders if you naively ran it entirely on the Ethereum mainnet. Costs like that would completely erode investor yield. Layer 2 solutions aren't just some nice-to-have upgrade. They are economically mandatory if you want to scale.
So issuers basically have two main paths here. They can use optimistic rollups like Base or Arbitrum. These execute transactions off-chain and post the compressed data back to Ethereum, slashing costs by like 95% while keeping that rock-solid Ethereum-level security. Or they can build custom app chains, like we discussed earlier. With an app chain, a chief financial officer can deploy a $2 billion fund and set their internal gas fees to exactly zero. That creates a perfectly fixed, predictable operational budget.
All right, we've reached our final architectural pillar in Section 4, securing the digital vault and protecting these tokenized assets. Because when you have $50 million managed purely by code on a public network, well, there was no FDIC hotline to call if things go wrong. And this brilliantly illustrates exactly why security is so paramount. The history of hacks in this space is just devastating. I mean, the Ronin Bridge lost $625 million due to poor multi-sig key hygiene. Wormhole lost $326 million to a signature verification bug. Mango Markets lost $117 million to simple Oracle manipulation. These aren't just historical curiosities. They're devastating multi-million-dollar cautionary lessons that prove, without a doubt, that sloppy architecture will absolutely be punished by attackers. So, how do you actually protect these assets? You use defense in depth. A single code audit is no longer enough. It is merely table stakes at this point. Serious platforms hire multiple independent security firms like Trail of Bits or Open Zeppelin. They use formal verification from companies like Certora to mathematically prove their smart contracts literally cannot be broken. And they make sure any contract upgrades require strict governance and mandatory on-chain time locks. This gives the community plenty of time to review changes before they ever go live.
Let's move over to Gnosis Safe and see how this builds into treasury management. If one single private key controls a massive digital vault, that is a terrifying single point of failure. The industry standard to prevent this is Gnosis Safe. It's a multi-signature wallet that requires a specific threshold, say 3 out of 5 independent signatories, to approve any movement of funds. You distribute those keys across different organizations, physical geographies, and hardware systems. It makes it exponentially harder for an attacker to compromise the vault.
Finally, while traditional insurance won't touch smart contract bugs, on-chain protocols are stepping in to fill the gap. Nexus Mutual is a prime example here, offering decentralized insurance backed by community underwriters. But, it's vital to note that while this is a fantastic complementary layer of defense, it remains pretty immature. The capacity just isn't quite there yet to fully ensure a billion-dollar institutional exposure.
So, we've unpacked the liquidity connectors, the oracles, the strict economics, and the totally unforgiving security demands of tokenized real-world assets. The blueprint is fully laid out, and the foundations are actively being built as we speak. But it leaves us with one massive, lingering question to end our explainer today. As this invisible digital architecture matures to handle trillions of dollars in real-world value, is traditional global finance truly ready to step away from legacy systems and completely trust the code? I'll let you ponder that one. Until next time, keep learning.